vector calculus, and we have to continue with that. In the last class, we have defined what is the vector point function and what is the scalar point function. Now, let us continue with that. Now, with the definition of a vector point function and scalar point function, we were able to define the definition of del, and your del was I cap del by del x plus g cap del by del y plus q cap del by del z. And this is the symbol which we use for a gradient of a vector. And what does it mean? Suppose we have a vector r, and the vector r is xi cap plus yg cap and plus zq cap. Then we can find out the gradients of a vector quantity. Gradient of a vector quantity will be that is I cap del by del x. Just put the value of a del, and then also said to be the gradient of a vector r in this case, and that is g cap del by del y and q cap del by del z. You have read the basics of vector calculus in the class of 10 plus 2 or probably in second semester also. So this is xi, yj and zk. So you can easily find out because I cap into I cap will be 1. So del by del x of x is come out to be 1, and del by del y of y come out to be 1, and del by del z come out to be 1. This come out to be 3, and this will be the case of a dot product, not a vector. Remember, this is the case of a dot. This is the divergence, not gradient. And gradient will be of a scalar quantity always, not of a vector quantity. This is the difference. In the case of divergence, we always find out the del of a vector quantity, and divergence of a vector quantity is always a scalar, but gradient of a scalar quantity. The scalar quantity may be any function. Suppose this is x square and plus y square and plus z square. So this is the scalar quantity we have. We can find out the gradient of this scalar quantity by using the definition of del. This is your definition of del. I cap del by del x, and that is g cap del by del y and p cap del by del z of this scalar quantity. And you know that what is this? This is the equation of a sphere. This will be the equation of a sphere. If we use with this, that is equal to minus 3 is there. Suppose you use minus 3 also. So if we are using the minus 3, then if we are using the minus 3 here, then what does it mean? This is the equation of a sphere. I'm writing down the equation. This is x square plus y square plus z square is equal to 3. This is the equation of a sphere with the center 0, 0, 0, and your radius is square root of 3. So you just put that is minus 3 here. So gradient of this scalar quantity will always be a vector. So I cap del by del x of this quantity. So the derivative of this quantity will with respect to x. That is 2x I cap, and similarly derivative with respect to y. That will be 2y j cap, and similarly 2z k cap. And this is the gradient of a scalar quantity. You can also write down gradient as graph of a scalar. Generally, graph is also written with del, but in case of divergence, we use dot here. But in case of we don't use the dot product here. So the versions of always a vector quantity, but gradient will always be of a scalar quantity. Always remember this point. Now, so let us continue with the directional derivative and a unit vector. These are the important terms we have. And the first question is you just to find out the unit vector, find out the unit vector. Okay. So let us continue with that. We have to find out the unit vector which is normal to the surface. We have the surface given to us, and the surface is x by q into z square is equal to 4. This is the surface given to us, and at the point -1, and 2. Just understand the statement of the question. You want to find out the unit vector normal to this surface at this point. First of all, in the solution of the question, you just name this surface as a function. So name this surface a function f. This is the function we have with. Now you would have to find out the vector normal to this surface. So therefore, a vector normal to f, the surface f, will always be equal to gradient of f. And gradient by definition, that is I cap del by del x, g cap del by del y, plus k cap del by del z of this surface f. The surface f is x y cube z square minus 4. Now we just find out the gradient of this. When you operate this term to this factor, you have to find out the derivative with respect to x. So ultimately what we have y cube z square I cap, and similarly that will be 3x y square z square g cap, and similarly derivative with respect to z will be 2x y cube z k cap. So this is your required gradient of the scalar quantity. Now we just need to find out the value of gradient of f at the point. The point is -1, and 2. Now you just need to put this point here. So -1 whole cube y cube will be -1 whole cube. That will be negative sign, and 2 square will be there, 4. So -4 I cap, and this will be that will be -3, and 2 square will be 4. That will be 12 g cap. And similarly put the values here. That will come out to be +2 into 2. That come out to be 4 g cap. So this will be your vector normal to the given surface. The surface is this one. So now for finding out the unit vector normal to the surface, for finding out the unit vector, you just need to do del f upon its magnitude. Magnitude means the modulus of the vector quantity. So modulus of the vector quantity will be square root of -4 square. That will be the coefficient of I cap square plus the coefficient of g cap square and the coefficient of k cap square. And in the numerator, you just have gradient of the vector, that is -4 I cap minus 12 g cap and plus 4 k. Now this is your vector, unit vector normal to the given surface. If you simplify it, you will get in the denominator we should have square root of 16 plus 144 and plus 16. So ultimately what we are left with, we are left with 32 and 44. That will come out to be 176. So that will be 176 square root, and in the numerator -4 can be taken common. I cap plus k cap minus k cap. This will be your numerator here, and you just need to calculate the square root of the term. If you remember, you want to find out the square root of the term. probably it will come out to be 15 square will be there. It should come out to be 4 4s are 16 and 4 4s are 16. Investment. The square root of 176, that will be 1. If you don't know how to find out square root, just recall the terms. You will have a 76, that will have 24. Now, you should have, you need to factorize the terms. The factorize there will be 16 into 11, I think so. And that will be minus 4 I cap plus 3j minus 3 cap. Square root is not possible here. You have to factorize the terms. Typically the factorization will be like this: 60 into 11 square root. So this is 16 square root. You know that the square root of 16 will be 4, 11 square root. This 4 will be cancelled with this. So this is your required unit vector, which is normal to the given surface. The surface was given to us and we named the surface as surface F. So by this way we will be able to find out the unit vector normal to a given surface. Now we must have one more question. The question is related to directional derivative. This is also very important question. This type of question come again and again in the final exams. So we have the surface given to us. Surface is a function of x, y, z, and the question is that is x, y square plus y, z cube. This is the surface, and at the point 2 minus 1, 1. This is the point. We just want to find out the directional derivative of this surface in the direction of this vector. The vector is I cap plus 2 j cap and 2 k cap. And for this, first of all, you need to find out the gradient of f. And the gradient of f will come out to be y square I cap, that will be 2x y plus z cube j cap, and that will be derivative with respect to z, that will be 3y z square k cap. And using the definition of del. This is the del operator, and we have defined the del operator earlier. The del operator was I cap del by del x, j cap del by del y, and k cap del by del x. This is the del operator. You must remember this. Now, this is your gradient of this surface. Now, at the point you need to find out the value of gradient. So the point is that is 2 minus 1, 1. Put the value here, that come out to be I cap, and this will come out to 2 and 2, that will be minus 4 and plus 1, that is minus 3 j cap. And we just use the value here also, that will come out to be minus 3 k cap. You can verify it. So this is the this is the gradient of the surface in the direction. No, not in the direction. This is the gradient of the surface at this point. Now we just need to find out the directional derivative. So directional derivative of the given surface. The given surface was f in the direction of and the direction is this vector. Your vector is I cap to j cap and to k cap, and that will be equal to this vector, that is the gradient vector. This is the procedure for finding out the directional derivative. This is the gradient into dot product. Remember, this will be the dot product with this vector, the vector, unit vector normal to this surface. So you just need to find out the unit vector of this. So finding out the unit vector normal to this surface, you should need to take the magnitude in the denominator, because this is the way to find out the unit vector normal to the surface. So you can find out the dot product now. I dot I is 1, so minus 3 into 2, that will come out to minus 6, and minus 3 into 2 is again minus 6, and divisible by 1 square, 2 square and 2 square. Denominator is 9 and square root of 9 is 3, and this comes out to be minus 11. So ultimately what will come out to be minus 11 upon 3. So this is the directional derivative. What does it mean? The directional derivative of a scalar point function is always in the direction of some vector. In the direction of some vector is always a scalar quantity. You just observe this. This is a scalar quantity. Now, suppose the same question is given to us. The question is this, and you have to find out the directional derivative of the given surface. Surface is also same, but in the direction of x-axis. Now, in the direction of x-axis, you need to find out the directional derivative. And you know that in the direction of x-axis, we always have the unit vector I cap. So in the direction of x-axis, the directional derivative, dd stands for directional derivative. I am repeating again. I am taking the same surface. It means gradient is same. The same gradient will be used here. This is the gradient vector. I cap minus 3 j cap minus 3 k cap. But remember, we need to find out the directional derivative of this vector in the direction of x-axis. So in the direction of x-axis, we just have I cap, and that is plus 0 j cap and 0 k cap. Just simply you just need to write in 0 0, and divided by its magnitude, and magnitude will be 1 square, 0 square and 0 square. Ultimately it will give you 1, and in the denominator there is 1, and in the numerator I dot I is 1, minus 3 into 0 will be 0, and minus 3 into 0 will be 0. So this is the directional derivative. Again it is the scalar quantity. So this is the directional derivative in the direction of x-axis. Now, suppose we want to find out the directional derivative in the direction of z-axis, and in the direction of z-axis, your vector will be only k cap, and what will be its magnitude, and that will be in the denominator there is 1 square. So minus 3 k cap dot k cap, that will be minus 3. Always remember, the dot product of a similar matrix always give you 1. I dot I is 1, j dot j is 1, and k dot k is 1. But I dot some another vector, suppose that is j, will always be 0. So the dot product of different vectors will always be 0, and dot product of similar vectors will always be 1. So this is the procedure by which we will be able to find out the directional derivative of different type of questions. Now, one more question we have. This is another example which you can do or find out. This type of questions are also very important. You just need to find out gradient of r raised to power n should be n r raised to power n minus 2 into vector r. This is what we need to do. This type of questions are very important. Prove that this example, gradient of r is to power n, and we know that what is the vector r? The vector r is a standard vector xi cap, yj cap, and z t cap. This is the standard one, and you just be able to find out the magnitude of this, and we know that that is x square, y square, z square. These values will never change, and you know that r modulus raised to power n, and what will come out to be x square, y square, z square raised to power n by 2 by using this definition. So all these terms are standard terms. You can use in any type of question. Whenever it is required, you can use the terms. So let us use on the left hand side. The left hand side is gradient of r raised to power n. And what is gradient? That is the definition of a del operator. I cap del by del x plus j cap del by del y plus k cap del by del z into will be this r raised to power n. So just write down here x square, y square, z square raised to power n by. So you always know that gradient of a scalar quantity, this is a scalar quantity, will always be a vector quantity. So what will be its output? It will be a vector. So let us operate it one by one. So del by del x of this term we want to find out, that is n by 2 x square plus y square plus z square raised to power n by 2 minus 1 into the derivative with respect to x, that is 2x I cap. This I cap is there, and similarly we can be able to find out that derivative with respect to y, and it will be x square, y square, z square raised to power n by 2 minus 1 into 2 by j cap, and the third term will also be similar, x square, y square, z square raised to power n by 2 minus 1 into 2z 2 cap. So if you observe the terms, you will see that 2 is cancelled in each of the terms. We can cancel the constant 2 in all the terms here, and if you see that is m x square plus y square plus z square raised to power n by 2 is there, and the denominator term is x square plus y square plus z square, because this negative one will come in the denominator. And you can see all these terms are there in each of the so if you can do it in common, and otherwise that is xi yj plus z3. And you know that what is the value of the denominator by this, and that is come out to be r. So what is x square plus y square plus z square? That is r square. Because this square root will go on the other side, and it will give you r square. And what is this? This is r square. This value is also r square raised to power n by 2. And what is this? This is vector r. You see. So use the values, and these two will be cancelled, and r raised to power n, and this 2 in the denominator and we put written here. N r raised to power n minus 2 into r vector. This is important. So there are many questions of this type which may come in the exam. Prove that the question comes like this. Prove that the identity. We can call this as identity. Now, let us take one more question. Suppose the question is find out the directional derivative. Find out the directional derivative. That is the directional derivative of let's write down the statement. Find out the directional derivative of the scalar point function x square yz plus 4xz square at the point 1 minus 2 and minus 1 in the direction of a unit vector in the direction of a vector 2I minus j cap minus 2 j cap. So we just find out the gradient of this scalar point function, that is 2x yz plus 4z square I cap, and the next one will be derivative with respect to y, that is x square z into j cap. Next one will be derivative with respect to z plus 8xz j cap. So this is the derivative. Now we just find out the value of the gradient at the given point. 1 minus 2 minus 1. Put the values here. That will give you plus 4, and that will give you plus 4. That comes out to be 8i. And x square is 1 square and z is minus 1, so minus j cap. 1 square y is minus 2, and that will be minus 8 and minus 10 j cap. So this is the gradient of a scalar point function, and we know that the gradient of a scalar point function is always be a vector quantity. So therefore the directional derivative of phi in the direction of given vector. The vector is 2I cap minus j cap minus 2 j cap. So this is the vector given to us, and we need to find out the directional derivative. The procedure as we have discussed earlier, that is 8I minus j minus 10k. Always remember, we want to find out the directional derivative in the direction. So the direction is important. It means we need to find out the unit vector normal to which direction. So dot product, that is 2I minus j minus 2k. We need its unit vector. So its unit vector will be 2 square minus 1 square plus minus 2 square. So this is the unit vector normal to the surface. And you just take the dot product. 8 into 2 will give you 16, and plus 1 and plus 20 will be there, and it is divisible by 3. But in the denominator you will get a square root of 9. So that will be 37 upon. So this is your required directional derivative. Always remember, what is the meaning of a directional derivative? The directional derivative is, suppose we are in 3D plane, and in a 3D, suppose we have a surface like this. This is a 3D surface, and the surface is lying in x, y, z plane. No doubt about that, because we just observe this surface in a 3D. The name of the surface is f, and this is the function of x, y, z. Now we must have, uh, because we are observing this surface in 3D, and we must have a vector. Suppose they say that we just find out the directional derivative in the direction of this vector. I am just drawing this. So directional derivative in this direction. Suppose obviously its vector will depend according to the position of this. So if we are in positive direction of x-axis, we must have x positive. X positive meaning. What I want to say, if you observe this one, this is the direction given to us, 2I minus j minus 2 3. If x-axis is on this side, and then we know that on the opposite of that we should have x negative side, and on the opposite of y we should have negative of y, and on the opposite of z we should have negative of z. So if the component of I cap is 2, which is a positive quantity, it means we are discussing about the direction in which we are moving toward a positive x-axis. So this means positive x-axis, so positive x-axis, and this means negative y-axis, and this means negative z-axis. So we are talking about, no doubt, we are talking about x, y, z plane. But x, y, z planes are also very important here. That which x, y, z plane. You can say that we are talking about x, y dash, z dash. Y dash means negative side of y, z dash means negative side of z. So this is important. So whenever a direction is given, so direction is important according to the positioning of a vector. Always remember that which direction we want to find out the directional derivative. Suppose they say that find out the directional derivative in this direction minus I plus j plus 5k. Now it is clear x-axis is negative, y-axis is positive, z-axis is positive. So I am talking about this plane. So in 3D you can visualize the surface, that we have a surface, no doubt about that. And the important is this surface is lying in x, y, z plane. And obviously if we are talking about 3D, we can take the example of a cubide. A room shape cubide is there, and a room shape in the room shape cubide we always have 6 faces: floor, roof, and all the four walls. So 6 faces of the cubide is there, and according to the positioning of the wall or roof or floor, we will decide about the positive side of x-axis or negative side of x-axis. So this is the meaning of a directional derivative. So we shall continue in the next class. I stop my class here, and on tomorrow we shall this is the